In traditional information retrieval, models like TF-IDF or BM25, which are based on the bag of words approach, represent their text in a very sparse format. This means they treat a document or query as just a bunch of words without considering their order. But these models have a long-standing problem with vocabulary mismatch. This happens when the relevant documents don't have the same terms as the ones in the query. So people have tried to replace these bag of words methods with learned neural rankers. Learning dense representation of text using approximate nearest neighbor search has shown really good results on several benchmarks. But since it can't explicitly match terms, it doesn't perform well in some cases, especially in zero-shot situations. To get around the downsides of earlier methods, more people are getting interested in learning sparse representations for queries and documents. By learning what's called term weights, models can keep the good stuff from bag of words models, like exact term matching, the efficiency of inverted indexes, and being easier to understand. Also, by using methods to expand terms, these models can help reduce the problem of vocabulary mismatch. One of the popular models for this type of sparse retrieval is called SPLADE. First, let's look at how we can get the term weights for each query and document in the SPLADE model. Imagine we have an input token sequence from T1 to Tn, and its corresponding BERT embeddings from H1 to Hn. To get the value of how much each token in BERT vocabulary is connected to the word in the input sequence, we can think of term importance factor, Wij, where token j from BERT's vocabulary and token I from the input sequence. In this context, EJ represents the BERT input embedding for token j. Keep in mind that token j could be any word from BERT's vocabulary, which means it could lead to the expansion of words in the sequence. The final representation for each token in the vocabulary is created by adding up the Wij values across the input sequence tokens. But first, ReLU is applied to make sure the term weights are positive. Before the summation, we also use log saturation. This helps prevent any one term from dominating and leads to a more sparse representation. We call this method SPLADE sum. By doing this, we can finally figure out the term weights for all the words in the vocabulary. We can also easily replace the sum into the max pooling operation to get better term weights. Experiments show that this simple change can significantly improve SPLADE's performance. We call this version SPLADE Max. This is an example where the model adjusts term weights by focusing on important terms and ignoring most of the terms that don't add useful information. Expansion helps to enrich documents either by automatically handling things like stemming, so adding the token lag from the original word lags, or by adding related topic words such as treatment. For ranking documents, we calculate the cosine similarities between the query and the document representation. The table shows how SPLADE performs in a zero-shot situation using a selection of datasets from the BEAR benchmark, which includes different datasets for testing zero-shot performance in information retrieval. The baselines are the top performing models from previous tests. You can see that SPLADE Max does better than the baselines, highlighting the strength of the SPLADE method for zero-shot retrieval. When building a retrieval model, it is important to consider not only the performance, but also how fast it can retrieve relevant information. This paper also explores the balance between efficiency and effectiveness. To improve efficiency, This paper introduces a document-only version of SPLADE where no query expansion or query term weighting is needed. We call this version SPLADE doc. Here, instead of calculating cosine similarities between the query and document representations, the ranking score is simply the sum of the term weights in the document that appear in the query. Since the ranking score only depends on the document's term weights, everything can be pre-computed offline, so the inference cost can be reduced while still having competitive results. Another way to improve efficiency is by adjusting the scale of document expansion. The figure shows how we can balance efficiency measured by the average size of document representations with effectiveness. You'll notice that more document expansion generally boosts performance, but it can also increase the number of floating point operations, creating a trade-off between two metrics. Today, I talked about how we can get term weights in SPLADE and how the expansion mechanism can impact the efficiency and also the effectiveness of retrieval. That's it for this video, and thank you for watching. I'll see you in the next video. Bye.